Hello and welcome back. Um, Today we're going to be looking at day 7. I took the day off yesterday, and day 6 was, I don't want to say trivial, but it was much easier, I think, than the previous days. So I'm not sure how much value it is on doing a video. If you want to see a video on day 6, um, let me know. But we're skipping to day 7 today. So for day 7, bunch of flavor text, but we're basically playing some variants of poker. So let's look at the input first. In the input, we get, there's 2 columns, and in the first column, there's going to be a bunch of hands. There's 5 cards in a hand, and let's see if it talks about the ordering. Yeah, so it goes ace, king, queen, jack, 10, which is denoted by these letters here. And then it sort of goes down from there all the way to 2. So ace is the highest and 2 is the lowest. And there's, when we're talking about hands, we can rank them, and this kind of follows the normal sort of poker ordering. But obviously you can't get 5 of a kind with a standard deck of cards. But anyway, the ranking for the hands goes 5 of a kind is the strongest, 4 of a kind is second, and then it goes full house, which is a group of 3 cards and a group of 2 cards. And then it goes 3 of a kind, 2 pairs, 1 pair, and then if each one of the cards are different, that's what they mean by high card here. So each one of the cards is different, and you're purely just looking at the strength of the high card. Which, by the way, high cards is also ranked or determined a bit differently than in a standard poker hand. Instead of, so the way that you break ties, assuming that you have hands that fall into the same category here, the way that you break ties is you look at the first card in each hand. So if you had, if you had a high card hand that starts with like 2, and you have a high card hand that starts with, I don't know, an ace or something. Well, let's say that you had a high card hand that started with 2, and is otherwise like a bunch of garbage. And sorry. Let's say that you have a high card hand that starts with 3 and is otherwise a bunch of garbage, and you have a high card hand that starts with 2 but happens to have an ace in there. Regardless of the fact that there's an ace in the second hand, the first hand is actually ranked higher, because you are comparing the cards in order, regardless of whichever one happens to have the highest card in it, if that makes sense. Okay, so part 1, and the second column in our input is like bid amounts, I guess. And so for part 1, the idea is that you basically order the hands by their, first by their hand rank, and then by their card ranks to break ties and so forth. And once you have a rank for each one of the hands, you multiply that rank with their bid amounts, and then you sum them. And that is part 1. So that's part 1, and we can look at part 2 a bit earlier, just because it makes things a little nicer. Part 2 says that the J cards are not jacks, they are now jokers. And jokers can be anything. And so, for example, in this hand, normally Q, JJ, Q2, normally this would be 2 pair. But if you replace the jokers with queens, this is actually 4 of a kind. So given that you apply this rule, and then also there's different ordering. So now jokers are considered the lowest card, lower than 2. So given these two changes, you do the same thing. You determine a rank for all the hands, and you multiply them by their bids, and then you sum them all up and you get your answer. Okay, so we'll start with the test inputs. Inget test.txt1. These are our hands. We can assign this to, well, we can, do I want to mix these? No, I want to split on spaces first. So does not equal partition right tack for each. That splits them into spaces. We can mix this to get a matrix. We can assign this to P. And then as long as we're here, we might as well pull out the left column, and we can assign that to H for hands. So we're just splitting the input on spaces here. And if we take the rightmost column of the input and we execute each one of these, then we get all the bid values. So we can assign those to B. So I think the first thing that we want to do is we want to write a function that, given a hand, will determine its hand rank. And if we look at all of the hand ranks, all of these are basically based on how many of the cards are the same. And so we want some sort of grouping operation. When we're talking about group in APL, the first thing you should reach for is the key operator. So key will, you can supply it a function, but basically the thing that you're running on is the actual element on the left side, and then a list of indices where the element occurs on the right side. So we have our hand values, and then for each one of these, we're going to write a function where we apply the key operator, and you can see the results of the function if I just do this. So we're pulling out all of the values in the left column, and then in the right column, as I said, you get a list of the indices. We don't actually care about the values that get pulled out or the indices themselves, so we can just do right tack length to just get the lengths of the various groups. And then I think it makes sense to sort these descending. So we want the highest values first. And then the really interesting thing is that if you just take the two first values, this is basically the lengths of the groups of the top two lengths of the groups of the cards. Let's say that. And if we look back at our hand rankings, so it goes 5 of a kind, 4 of a kind, full house, etc. These hand rankings would look like, so first of all, 5 of a kind, if we run this on like QQ, QQ, because we're doing two take, it will kind of pad the array with zeros. So our hand rankings would look like 5-0 for 5 of a kind, 4-1 for 4 of a kind, and then 3-2 for full house, 3-1 for 3 of a kind, 2-2 for 2 pair, and 2-1 for just a single pair, and then otherwise all of the cards are distinct. And if we sort these, you can see that all of these if you sort on all of these, you don't have to keep like a separate array of all of the the hand categories. You can just look at the first two elements here. You can see that these are already sorted. So basically, without having to encode any extra information about the hand categories, we can just use this function and look at the first two values of the sorted lengths of the groups of the cards. So hopefully that makes sense. And we can make it even nicer. So we'll run this on H. And rather than having a 2-element vector, we can do 10 decodes to compose them into a single 2-digit number. And so these numbers can be sorted on to get hand ranks. And it's just like, it's a very nice way to determine hand ranks. It will come in handy when we're sorting. So we'll call this like F, I guess, for function. Naming is hard as always, but this is our hand rank function. So when we're talking about sorting hands, we want to sort on hand rank first, and then we want to sort on the card rank. So to get the card rank, we can look at quad D, and if we drop the first of 2 values, we get the characters 2 through 9. And then on the ends, we can append 10, Jack, Queen, King, Ace. And this gives us kind of our ranking for the different cards. We can call this R for rank, I suppose. And then let's write a function that basically, given a list of hand ranks on the right side, and then given an array of the card ranks on the left side, because this is going to change from part 1 to part 2. Remember that in part 2, we're changing the order so that J's are actually the lowest. So let's write a function. We'll get R. So we can get the hand ranks for each one of our hands by just applying F here. And then if we do R on the left side, we'll write a function to basically sort all of the hands and apply the bidding values. So this will give us our actual part 1 and part 2 answers. First thing that I'd like to do is we can mix H to get a matrix, and then we can do alpha index of, and this basically finds the index of all of the characters in the left argument, which is the ranking string that we're supplying. And then we can prepend our hand rankings to each one of these. And so now we get this six column matrix. And if we sort on this, the way that sorting will work is it will first look at the first column, so it'll sort on the hand ranks first. And then if there are ties, it will go in lexicographic order for the remaining numbers. There is an article about total array ordering on the APL wiki. You can look into this, but basically Dyalog has, you can apply sorting on pretty much any array that you throw at it. So it can be strings, numbers, whatever you want. And but basically what we are concerned with is the fact that sorting will work from left to right on all of the columns. So it'll look at the hand rank first, and then the card ranks, which is what we want. So we can apply grade up to sort this. Grade, keep in mind, doesn't actually sort the thing that you're giving it. It gives you a list of indices where if you index into it, it will sort whatever you're trying to sort. So you can see here that we have sorted all of our hands by first hand rank and then card rank. So this one would be high card. It doesn't contain any pairs. This one has 2 pairs. This one also has 2 pairs, but this second K is higher than the T. This one is 3 of a kind, and this one is also 3 of a kind, but Q is higher than T, right? So we basically supplied a total rank for all of our hands, and now we're going to do something interesting, which is a double grade up. To give more detail about what this actually does, there's a really nice diagram on that Marshall Lockbaum, I think I'm pronouncing that right, put together for BQN, and it basically talks about what happens when you do a double grade up. So when you do a single grade, you can think of it as for each slot in this vector, you get an index that says where the element should come from in order to give you a sorted array, right? But there's not actually any relation to your initial elements here. In order to get a relation to your initial element, you do a double grade up, and this sorts this permutation, and then this resulting vector tells you kind of where each element in your initial list would appear if your array was sorted. So by doing double grade up, we can see that S would be the third element. We're in index 0 here. O would be the first, R would be the second, and T would be the fourth. So by doing double grade up, it allows us to get information about the relative order of the thing that you're sorting on, rather than a sorting permutation vector. It's a little bit hard to wrap your head around. I really recommend this article. It goes into some more detail and gives some more examples if you are interested. But for us, what this basically means is that by doing double grade up, we get the kind of ranks of each one of our original hands, and now we can just multiply our bid values by that, and we can sum them to get our part 1 and part 2 answers. So 6440, if we look at the answer for part 1 for the test input, yep, that is correct. For part 2, things are going to get a little more interesting. For right now, let's assign this to G, I guess. And then in order to get our part 1 answers, we do G on our initial rank and the hand ranks given by applying F on each cell. And we get our part 1 answer, right? Now for part 2, we have to figure out what the hand ranks would be if we replace the jacks or jokers with really any other card. There's probably more efficient ways that you can do this, but our input for our actual problem input is only 1,000 lines long, and the length of our rank here is 13. So if we basically tried all the possible combinations of substitutions, then we would only be doing it, 13,000 times, which is totally feasible to do. So given our ranks, and then given our hands, let's do an outer product, and we'll be constructing some function here. So we have our hands on the right side. We have the different characters for all of the card ranks on the left side, and we can just replace. So we supply supply a function that results in a Boolean vector here, we're going to use at, which allows you to do, it will allow you to run functions or provide replacement values either at specific indices, or you can give it a function that results in a Boolean vector. And let's see, we want to replace those with the characters on the left. And actually, do I even need to supply this? No, apparently that works. Okay. So you can see, so if we look at our hands, if we just look at our hands, we can see that the second and the fourth and fifth hands all have J's or jokers in them. And if we do this outer product, we can sort of see, so in the second hand, it goes from 2, 3, 4, 5, these all change, right? In the second hand here, this is counting from 2 up. And then in the last hand, we can see that this is counting from 2 up, right? So basically, we run all the possible substitutions for J in our hands, and then we can just apply F here to get the hand ranks. And we can see that if we do this, basically our fourth card on some value for J improves to 4 of a kind, as does our last value, as does our second value. And so to find the best possible hands for the substitution of all the jokers, we can just do a maximum reduce first to reduce along the columns. So these are all of the best possible hand ranks if we substitute J with any other value. And so those are the hand ranks that we're going to be using for part 2. And the last thing that we need to do is, if we look at our card ranks, we need to change it so that jokers are now valued last. So we can just do R without J to remove that value. And then we can prepend J so that now J is considered the lowest possible value, right? So if we do this, and that gives us our modified ranking, and if we run G on the best possible hand ranks for all of the J substitutions, we get our part 2 answer. It's 5905 for part 2, which is indeed the answer for the test input. So yeah, basically we're just doing a substitution for all possible values for J. By the way, this pattern of like, I think of this almost as like expansion and contraction. This is very common in array-based programming. I did this also in day 1, I think, where I was checking for all the possible substrings. Basically, you start with an array, and you expand that array in some way. Let's do that. You expand the array in some way, and then you compress the array by doing some sort of reduction. And this pattern comes up, again and again, at least in additive code problems and probably in array programming in general. This is just, something to internalize and keep in your toolbox. Okay, if you put everything together, you get this. This is golfed a little bit. We have statements on the same line separated by these diamonds, which are sort of like semicolons or statement terminators in other languages. But if we run this on our actual inputs, we get 246, 409, 899 for part 1, which is the answer, and then 244, 84, 8487, which is the answer for part 2. And this line, by the way, runs more or less instantly. So yeah, if we look at the size of the input, it's 1,000. When we do this outer product, the resulting shape is 13 by 1,000. So 13,000 comparisons, which isn't too much for modern hardware anyway. So that is day 7. Yeah, I think this is kind of an interesting problem. We're able to. There's a couple cool tricks here. So first of all, with the hand ranking, by just looking at the first 2 values and base 10 decoding them, we get nice numbers that we're able to we're able to sort on. And then this trick with the double grade up to be able to get the ranks of all of the hands without any additional indexing or any of this stuff is also pretty cool. And then, as I pointed out, this pattern of like outer product followed by some sort of reduction is something that comes up again and again. So it should be something that you reach for or keep in your toolbox. Cool. So that's day 7, and we will keep rolling. Thanks for watching.